everyone. Let me check all my audio levels and then we can just start. One person in the chat. Hello. Okay, it looks good. All right, so uh, let's just begin. I've got 5 questions today, which should cover all of the material that we did. And for Newton's laws, there's going to be just some qualitative questions on the test, and that's what my first question is going to be all about. But then there's also going to be the kinds of quantitative laws or quantitative applications of Newton's laws, which are like the masses on inclined planes and masses attached by ropes and things like that. And then a qualitative understanding of Kepler's laws, along with just the third law is the only one that I expect you to do some problems on, some quantitative problems on, and we'll do one of those. And then for energy, we did things like cars rolling up and downhill, and also the simple harmonic oscillator. Okay, now the only thing that I did in class that I'm not going to do today, it's the only other thing that you might expect to see on the test that I didn't quite do, is I didn't combine a car going up and downhill and a spring where you have both gravitational and spring potential energy, but we did quite a few of those in class. So I just thought I didn't want to like overdo that kind of question, so I picked something else. Okay, and there it is. Let's begin then. Okay, so the first thing is that you need to have a good intuition into Newton's 3 laws. Okay, and that means that you should not only be able to just state them, but like be able to recognize when the first law is applicable, when the second law is applicable, when the third law is applicable to particular situations, particular physical situations. Now, you should have them memorized, or at least semi-memorized, okay, that you would be able to state them. But the test is multiple choice. That's not something, the kind of question that I would ask. But nonetheless, if you don't have them in your head, semi-memorized, then when it comes to answering some of these questions, you might find them difficult. Okay, so what are the 3 laws? Like, how would you state them? The first law, the way Newton stated it, was that in the absence of any net force, an object that's at rest stays at rest, or an object that's moving at constant speed in one direction along a line continues to move at constant speed along a line. Okay, now that's equivalent to saying if there's no net force, there's no acceleration. All right, but Newton wanted to really emphasize that this idea of no net force means that there's no change in the state of the object. So if there's no net force, and the object's at rest, it stays at rest. And if the object is moving along a straight line, it continues moving at the same speed along a straight line. Okay, and the straight line there is important because if it's going around a corner, it's accelerating, and that's uniform circular motion. Okay, so there's the first law. The second law says what happens if there is a net force. So if there is a net force, the object accelerates in the direction of the net force, according to the formula F net equals ma. Okay, or you can also state it as A is equal to F net divided by m. All right, so that's the second law tells you what happens if there is a net force. All right, and the second law is the most important, so we really need to understand it. What does this word net mean? Net means that there may be multiple forces acting on an object, and a force is any push or pull. So there might be a lot of things that are pushing or pulling on the object. Okay, and it's not any one force, but it's the sum total of all of them as a vector, which gives rise to this net force, and the net force causes the acceleration. Okay, so the acceleration isn't in the direction of any one of the forces, it's in the direction of the net force. Okay, and then to do the calculation, like to actually do the numerics, it's F net equals ma. All right, and then the other thing with Newton's second law is what is mass. Okay, and mass is the amount of substance present. All right, that's m, the amount of substance present, and you measure the mass using a balance. In other words, you measure mass by comparing one mass to another mass. Okay, that's different than weight. So the weight of something is the force of gravity on the object, and that you measure by using a spring. Okay, in other words, like it's like you attach the mass to the spring, you see how much it stretches the spring, and it's not the same as the amount of mass because the amount of mass is invariant. The amount of substance present is invariant no matter where you are in space. But the force of gravity on the object does depend on where you are. So if you're on the surface of the Earth, something might weigh 100 newtons. Okay, but on the moon it would only weigh 16 newtons. Okay, and in empty space it would weigh 0 newtons, the same object. But the same object has just as much mass in all three situations, but it has a different weight because the weight depends on the force of gravity. Okay, or the weight is the force of gravity. Okay, so once again, to measure the mass, you use a balance. And if it balances on Earth, it'll balance on the moon, it'll balance on Jupiter, wherever, okay? So to measure mass, you use a balance. To measure weight, you use a spring, okay? And the relationship between the two is if you have the mass, you can calculate the weight because the weight is equal to mg, all right? Which you're going to see in the problems that I'm going to do in a minute anyhow, all right? So there's the second law in full explanation, okay? And finally, what's the third law say? The third law says if object A pushes on object B, or better yet, if object A exerts a force on object B, then object B exerts a force on object A equal to magnitude, opposite in direction. Okay, so have those in your mind. All right, I know the test is open book, but have those in your mind because in the middle of the test, you're going to want to have the understanding of those ideas at hand, not something that you're going to try to learn during the test. Okay, so let me see if there's any questions in the chat. Nope. All right. So here's some typical questions that you might see. Okay. So I stated them, but like what kind of question would you see on the test? So here's one question. If an object is seen at rest, what can you conclude about the forces acting on that object? Okay. So you see this object, it's just resting there. What can you conclude about the forces on that object? Okay. All you can conclude is that the net force is equal to 0. All right, the net force is equal to 0 because of Newton's first law. Newton's first law says if the net force is 0 and the object's at rest, then the object stays at rest. So if you see an object and it's not moving, you can't say there are no forces on it. There might be lots of forces on it, but the sum of all those forces is going to add up to 0. Okay, so there you go. There's an example of the first law. Okay, so if an object is seen at rest, and to emphasize it, I might have even put and stays at rest, okay? What can you conclude about the forces acting on the object? The sum of all the forces must be 0, or F net must be 0. Okay, let's go on to the second one. And, with a multiple choice test, what would I do? I would, have all different possible things that you might conclude, things that are absurd, and then you'd have to pick the right one. Okay, so if an object is seen moving at constant speed in a straight line, what can you conclude about the forces on the object? Well, it's also the first law, isn't it? Because if the net force is 0, then an object which is moving at constant speed in a straight line continues moving at constant speed in a straight line. Okay, so once again, you see this object, it's moving at constant speed in a straight line, and you can conclude that the net force is 0. Okay, constant speed by itself is not enough because it might be constant speed but going around a corner, and like you could feel it even in a car. When you go around a corner, you can feel that centripetal acceleration, and corresponding to that centripetal acceleration is some net force. Okay, so it's not enough to be just constant speed, it's constant speed in a straight line. So if an object is moving at constant speed in a straight line, then the net force must be 0. Okay, so there's the first two, A and B, were actually the first law. Okay, all right, so here we have another question that I could ask. If an object has a net force acting on it to the right, what can you conclude? Okay, so there's some object, and there's a couple of directions like left, right. Okay, and there's a net force acting on this object to the right. What can you conclude? Well, it's going to accelerate. All right, because there is a net force, it's going to accelerate. That's the second law. And it's going to accelerate in the direction of the net force. It's also going to accelerate to the right. Okay, so applying the second law, the answer would be the object will accelerate to the right. Okay, so if an object has a net force acting on it to the right, you can conclude that it will accelerate to the right. Okay, and well, there you go. I mean, these are just qualitative, so I'm not giving any numbers here. It's just seeing if you understand it. Like I might on the test, like question A, it would stand still. Well, no, that's wrong, because if there's a net force, it accelerates. Okay. Another possibility would be it accelerates to the left. No, it has to accelerate in the same direction as the net force, so it would accelerate to the right, and so on. Okay. So, if you know those three laws, you should be able to answer those. You should be able to identify the correct answer out of the five possibilities. Okay. Last question. If a big person pulls on a small person, what can you conclude? Okay. The third law says if object A exerts a force on object B, then object B exerts a force on object A equal in magnitude, opposite in direction. Okay, that equal in magnitude is sometimes the part that's not intuitive, because if you have a big person pulling on a small person, you might say, well, the big person pulls with more force than the small person. Okay, like an adult and a child or something like that. You might say, oh, they're playing tug of war, and the child's pulling on the adult and the adult is pulling on the child. And you say, well, who's pulling harder? And a lot of people might say, well, the adult is pulling harder because they're stronger. But no, that's not what the third law says. The third law says that they both pull on one another with the same magnitude force. Okay, so if the adult pulls on the child with a force of 100 newtons, then the child pulls back on the adult with a force of 100 newton in the opposite direction. Okay, and so the intuition here with the third law, it's pretty intuitive, but the intuition kind of breaks down when one object is really big and the other one's really small. The most extreme example of this is me and the Earth, or an object in the Earth. The Earth is pulling me down with about 1,000 newtons of force pulling me down. I'm pulling up on the Earth with 1,000 newtons of force, and I can definitely feel the Earth pulling me down with 1,000 newtons of force. And if I were to jump off of like I don't know, like from the first floor, jump out of a window on the first floor, I would certainly know that the Earth is pulling me with 1,000 newtons of force because I would fall towards the Earth. But the funny thing is that I'm also pulling the Earth up with 1,000 newtons of force. So isn't the Earth falling up towards me? The answer is yes, but the Earth's mass is so huge that 1,000 newtons of force does barely anything to move it. So there your intuition seems to fall apart completely, because you say, no, the Earth doesn't move, or there is no force on the Earth. There is. It's 1,000 newtons, but 1,000 newtons compared to the billions of kilograms of mass that the Earth is nothing. Okay, so that's why your intuition kind of falls apart when one object is big and the other one is small. But the force that the two objects exert on one another is equal in magnitude, just opposite in direction. Okay, that's enough, I think, for the qualitative questions, and let's move on to some quantitative questions. Let me see here. All right, still one person watching, but no questions. All right, so this is the type of problems that we did in class, and in this problem I tried to cover all the possibilities. Okay, so let's read the question. We place a 15 kilogram block on a frictionless plane inclined at 20 degrees. It is attached to a 6 kilogram mass dangling off of the end as shown. We'll look at the diagram in a minute. What is the direction and magnitude of the acceleration of the system? Okay, so read it one more time and then we'll look at the picture. A 15 kilogram block on a frictionless plane inclined at 20 degrees, and it's attached to a 6 kilogram mass by a rope. Okay, as shown. We'll look in a minute. And what's the direction and magnitude of the acceleration? Okay, so here's the picture. All right, there we go. And you can see this this plane here. All right, and there's the 15 kilogram mass on the plane, and it's attached by this red rope to the 6 kilogram mass dangling off of the end as shown. And the question is, how fast does this system accelerate? For part A, there is no friction. For part B, there's going to be kinetic friction, and for part C, there's going to be static friction. Okay, so how do you proceed with these? Well, this one has two objects. Okay, so there are two bodies here. There's this one right there, the 15 kilogram mass, and then there's the 6 kilogram mass there, like that. Okay, so you have to do the free body diagram for each of them. And normally I wouldn't do both free body diagrams on the same thing. I would like isolate them and try to draw separate diagrams so I don't get confused. But I think here we might, if we go carefully, we can just draw a free body diagram for the 15 kilogram right here locally on the diagram, and then similarly here. Okay, so what's happening here? What's happening? Well, with the 15 kilogram mass, there is the force of gravity, and let me do forces in blue here, like this. The force of gravity is straight down like that. Okay, so there's the force of gravity straight down. But you know that if you do that, then you're going to get in trouble, because as soon as you draw the normal force, and you'll draw the normal force like this, okay, you see that those two forces are yeah, neither parallel to one another or anti-parallel to one another, nor perpendicular. And since you have to do the net force as a vector sum, you really need to break this up. Okay, you really need to break up one or the other, and it's easier to break up the gravitational piece. So there's this one here, okay, and there's that piece there, okay. And you go, well, which one's which? This one is mg cosine theta, okay, and this one is mg sine theta. All right, like that. Okay, and theta, by the way, is at 20 degrees, which is right there. Okay, we'll put the numbers in a minute. Let's just get, kind of a template diagram going. All right. And sometimes people say, well, like they'll say, I confuse the sine and the cosine. Okay. Well, the way I remember this is that sine goes to 0 when theta is 0. If this were totally flat, like imagine making theta smaller and smaller and smaller until it becomes flat. Well, if theta is 0, then this one should disappear completely. Okay, and it's the sine that goes to 0 when theta goes to 0. Okay, so when theta is 0, sine is 0. Okay, and that's how I remember that the component which is parallel to the plane is the sine. Okay, conversely, when theta goes to 0, the cosine becomes 1, and then you just go back to the weight of mg. Okay, I hope that helps. I mean, that's the way I remember it. Okay, however you want to remember it, there it is. Okay, so there you go. There's the force of gravity. That is one force, but broken into its two components, broken into a component parallel to the inclined plane and perpendicular to the inclined plane. Okay, so this one's the perpendicular, and this one is the parallel. Okay, what other forces are there? Well, there's the normal force, which is, I drew it a minute ago, but there it is there like that, and we give it the name Fn, like that. And then there is a tension up like this, Ft. Okay. All right, we'll put numbers in a minute, but since we're at it, we might as well do the free body diagram for the other mass. Okay, so the 6 kilogram mass, it has a mass down here of mg. Okay, but maybe we should be very careful here rather than calling it mg. See, the danger in calling this mg is that now you have two mg's. You have this mg and you have that mg, but this mg over here, that one you want to put in 15, and the other one you want to put in 6. So maybe we should call this one mg1, and it needs a 1 there like that. And this one we can call mg2 like that. Okay, there you go. All right, and all right, so we have the weight of that 6 kilogram mass. And there's also, if there were just a weight, this thing would be free falling. Well, it's not free falling because there is the tension up like that, and that one's Ft. Okay, like that. All right, so Ft up. Now, last thing before we switch back to the other screen, this Ft and that Ft are equal. They're equal. We don't know how big they are. We'll find out as we solve the problem, but they are equal to one another. The reason is the Newton's third law. Okay, and remember, maybe I'll draw it up here. If you have object A, so this is like object A here. Okay, and you have object B here like this. Newton's third law says, there's a force this way. So B is pulling A that way. We can call that Ft, and A is pulling B in the opposite direction. We can call that Ft. And Newton's third law says that these are equal to one another. So this one is equal to that one. And Newton's third law also says that they're in opposite directions. So this one is in the opposite direction of that one. And you go, okay, well, you just said a minute ago that these two are equal. That one is equal to that one, but they're not in opposite directions. This one's kind of parallel to the plane and this one's straight up. And you go, well, what's going on? Well, a proper analysis would have to include that pulley there, okay? And so the pulley, without going into all the details, because you'd have to actually have to apply Newton's third law there too, okay? But that pulley, you could just say the net effect of it is to change the direction, but not the magnitude. Okay, that's what the pulley's doing. So yeah, this Ft really is equal to that Ft there, like that. Okay, and then one more thing before we go on, and that is you know, we're going to have an acceleration here, but you don't know the direction of the acceleration. Is it going to be uphill or is it going to be downhill? And you know what? I'll tell you what the direction is. It's actually uphill. We did one in class where we had it the opposite direction. And if we have it the opposite direction, if we choose by accident, you know, A in the opposite direction, then when we do the calculation, A will come out negative. Okay, so I did one of those in class. So here what I'm going to do is I'm actually going to say, look, I'm going to guess that the direction is, you know, uphill for the 15 kilogram. It's going to accelerate uphill for the 15 kilogram, and it's going to the 6 kilogram is going to drop. Okay, and that turns out to be the correct guess, and you'll see that A works out. Okay, so let's start putting in some numbers here. Okay, let's start with this one, mg cosine theta. All right, and so over here, I'll do the solution right here. So we have FMG, or you could, yeah, FMG, sorry, mg cosine theta, and I have to write out the theta like that, okay? This is the perpendicular component of gravity. It's going to be 15 kilograms, right? Because that's the block on the plane. Okay, 15 kilograms multiplied by 9.8, rounded off to 10, and then the cosine of 20 degrees like that. Okay, and I purposely didn't do these problems to start with because I kind of want to do them on the fly. Otherwise, you won't see all of my reasoning. One of the reasons I do this is to just like show you everything that I do as I think out these problems. Okay, so I just did that on my calculator, and here's what I get. I get that is 140.95 newtons. Now, you know, that's more digits than we need. You know, I would round that off on the test to 141. But, you know, as an intermediate answer, that's fine. You can keep more digits. In fact, it's good to keep more digits. This way you tend to avoid round-off errors. Okay, that is the perpendicular component. You can even write it here. Perpendicular weight. Okay. The component of gravity perpendicular. All right, now what? Well, same thing, but for the parallel component. And the parallel component, everything. The only thing that changes is that this is sine instead of cosine. All right, and let me do that calculation here. Oh, it did not like how I formatted that. It still doesn't like it. All right, see if this works. 20 degrees. Yeah, that worked. Okay, and I'm getting 51.3 newtons like that. Okay. All right, so we got those two. If we want, we can actually, at this point, start switching back and like writing numbers into the diagram, okay? So let's just remember it's like 141 and 51, okay? So over here, this one, let me put the numbers in red. This one was 141 newtons, okay? And this one was 51 newtons like this. Okay, and now we can conclude that Fn, see these two have to compete against one another, the mg cosine theta and the Fn, and neither can win. Otherwise, you know, it's going to accelerate in the wrong direction. So that Fn, whoops, let's switch to red here. That Fn must also be 141 newtons like that. Okay, and the Ft we just don't know right now. We just don't know. Okay, and so switching back here, okay, so we can now say, look, Fn, the normal force, must equal the same as the perpendicular component, like this. Okay, maybe I should just label here, this is the parallel mg, or the parallel weight, All right, like that. This is the normal, okay, and ft we don't know. All right, now when we add all of these together, we have to add them as a vector. And so if you go back here, the Fn and the mg cosine theta, they cancel. Okay. Now Ft has to be bigger than the 51 newtons because Ft is succeeding in pulling A uphill. Okay. So the net force here must be Ft minus 51. Ft minus 51. Okay. So over here, we can write that F net must equal the Ft minus the 51 newtons, or we'll write it out 51.30 newtons, like that. Okay, that is your F net for number one. Oh, and by the way, I probably should have put here mg1 like that, just mg1. All right, to not confuse it with mg2, which we'll have in a minute. There you go, there's F net. This is the point at which students often get confused. They go, well, what do I do next? The whole point of this diagram, the whole point of the free body diagram was to get F net. Okay, and there we go, we got F net. Now what? Well, F net must equal MA. All right, now there's two M's, so it's actually M1A. This second equality right there, maybe I can do like a double equals. I know that looks a little funny, but just to emphasize, that double equals right there, that's because of Newton's second law. This equals is because you did a vector sum and you found that, you know, the total force adds up to Ft minus 51.3. But then once you've got that total force, you can, just because Newton said so, you know, and Newton's right, okay, so just because Newton said so, that net force must equal Ma, like that. Okay, and so we know what M is equal to. It's 15 times A, and so you get your first equation, Ft minus 51.30 is equal to 15 times A. All right, call that equation number one, and you can't go any further. You can't go any further because you don't have Ft and you don't have A. We're trying to solve for A. And I didn't ask in the question, but once you get A, you can also get Ft. So, you know, in these questions, I always emphasize A, but don't forget, I could also say, well, give me Ft as well. You know, what's Ft equal to? Okay, so we'll do both. We'll do both. It's not that hard. Okay, so great. What did we do here? Let's just see. Well, we identified as far as we could the values of all the forces. Then we got F net, and we set that equal to MA, and we went as far as we could with that. Okay, you do the exact same thing with the second free body diagram. It's always like that. Identify all the forces, add them up as a vector, get F net, set that equal to MA. Okay, so back to this, and let's do that over here. Now over here, we've got M2G, and M2 is 6 times. I can actually write that in here because it's easy enough to do. I don't have to do it on the other thing. So, you know, M2 is 6, okay, and G is 10, and so you get that this thing has a mass of 60 newtons, like that, okay? All right, so M2G is 60 newtons. Ft is, again, unknown. We don't know it. We can, you know, well, we don't have to put a question mark there, but this, you know, this one here is a question mark. And this one here is a question mark so far. But we do know that that 60 newtons has to be bigger than Ft. Why? Because take a look. A is downwards. So that means that that 60 newtons is beating, it's overcoming the Ft, which is up. All right. If Ft were bigger, then it would accelerate up. Okay, but it's accelerating down, and therefore Ft must be smaller than 60 newtons. Okay, so that's it for the free body diagram. It's just two forces, one of which is still unknown, and the 60 newtons must be bigger than the Ft. Okay, so switch back to here, and so we can actually say over here, this first part was free body diagram 1. Okay, this one's from free body diagram 2. And what can we conclude? Well, we conclude that the 60 minus F net, I better put F net here, F net is equal to the 60 minus Ft, okay? And again, the 60 has to be bigger than the Ft because it's pulling it down. And then what's that got to equal? All right, so this is Newton's second law. Here it must equal M2A, and we know M2, we don't know A. M2 is 6, and A like that, okay? And then cleaning that up, you get that 60 minus Ft is equal to 6A like that, okay? And here's our equation number 2. All right. So, the easiest way to do these, because there are two equations and two unknowns, okay? You could play the game of like isolating and substituting, but just add the left-hand side and right-hand side of 1 and 2, okay? And what happens when you do that, I mean, I could just show you. There's the left-hand side of 1, okay? So we're going to take the left-hand side of 1, and we're just going to add to it the left-hand side of 2, okay? And you can already see that the FT will cancel out. So that's why this technique is nice, because it just makes it easier than having to, isolate FT and substitute in. Okay, so great, there's that. And then we have to add the right-hand side. So here we have 15, and here we have 6, like that. And so there we've added the right-hand side of 1 and 2, okay? And cleaning that up a bit, we get the FT's cancel, so we just have that, is equal to, and the 15a plus 6a is going to equal 21a, like this. And let me do this on the calculator. See what I get. And it looks like 8.7. Okay, so I get 8.7 here is equal to 21 times a, and therefore a is equal to divide that by 21. Whoops. Messing up here. Okay, divided by 21 is this number right here. Okay, meters per second squared. All right, so that answers the question. What is the acceleration? Okay, it came out positive, and that means that if we go back to the diagram here, see how we chose a up like this? All right, we chose a up like that, and then to be consistent, this a had to be down like that. Okay, let me do that in purple so you can see it a little bit better. Yeah, see the a there up, that has to, and that matches the a down like that. That direction was a guess, but it turned out to be the correct guess. Okay, and that's why a came out positive. All right. Okay, so now what? I didn't ask in the question, but since we're doing this together, now you can actually calculate what FT is. So part of the question I could have asked, well, what's FT equal to? Okay, and at this point you could either use equation 1 or 2. Okay, doesn't matter which one because they're both just as much work to find FT. So here we'll say use equation. I don't know. We'll use 2. Why not? To find FT. Okay, so we take equation 2 here like this. There it is. Okay, and we now know what a is equal to. All right, so we don't know this side, but we do know that a is equal to 6 times, well, 6 is the mass. Oh, hold on. And a is this number right here. Okay, which is equal to, let me see if I can do that on my calculator. It's equal to this. All right, and that's newtons. Okay, and then we can have to add FT to both sides, so we'll just get 60 here is equal to FT plus 2.484, and then we can subtract 2.484 from both sides. So we're subtracting this from both sides, and we will get 60 minus 2.484, and that's going to equal that number right there, which I will round off to that. Okay, there we go. So that is the value of FT. Okay, so actually this is something we didn't do in class and we can do now. Remember, we at one point assumed that FT was bigger than a certain value and smaller than a certain value. We now don't know that FT is equal to 57.5. Let's go back to that diagram and see if everything is consistent. So over here, we know that, let me do it in, I don't know if you can see orange. Let me see if you can see orange here. Yeah, it's okay. So we know that that's equal to 57 point, what did I say again? 57.5, okay? So we know that this is equal to 57.5, and we know that this is equal to 57.5, like that, okay? Now, we said that this has to be bigger than that. Otherwise, it wouldn't be pulled uphill, right? There it is being pulled uphill. So is 57.5 bigger than the 51 so that it gets pulled uphill? Yeah, it is. So that's consistent. And we also said that the 60 newtons has to be bigger than Ft in order for this to be going down or being pulled down, okay? And so is 60 bigger than the 57.5 so that it gets pulled down? And the answer is yes. Okay, so you can see that everything is consistent. All right, great. All right, so that answers the question and more. All right, that answers the question and more. And so let me go up here. Oh, no, sorry, it's below here. Okay, and now I change the question on you. Okay, I change the question. I say if the system is found to accelerate with only 0.2 meters per second squared, what is the coefficient of kinetic friction? Okay, well, let's think about this. Does the question make sense? Do the numbers make sense? Well, without friction, we found that this thing was accelerating at 0.414, okay, meters per second squared uphill. Now it's only accelerating at 0.2 meters per second meters per second squared uphill. Okay, so like that's less. So why is it accelerating less? And that is because there's friction. Okay, and so you really have to redo the diagram from scratch, but a lot of it is recyclable. So I'm not going to totally redo the free body diagram. Let's think through what has to change, but you have to think through everything that might change because you know, it is different now. We have a different acceleration. Things have changed. So to make sure that you don't miss some change, rethink every part of it. Okay, so over here, let me rub off that 57.5 because that's going to be wrong. Okay, so now let's think through here. We began with the blue. Okay, so just try to ignore the red numbers here for a minute. Okay, we have those blue, and we said, well, there's gravity, and the gravity was, you know, in two components, the perpendicular and the parallel component. There was the normal force and there was tension, but now there's friction. Okay, and the friction could either be, you know, pulling uphill or pulling downhill. But since this is being accelerated uphill, okay, since this is being accelerated uphill, the force of friction must be downhill. Okay, so think about it. It's accelerating uphill, so it's being pulled uphill. It's starting to move uphill. Okay, and the force of friction is always in the opposite direction of the motion. Okay, force of kinetic friction, and so there must be a force of friction down this way, like this. All right, FF, like that. All right, and you say, well, how big is it? Because we don't know FT. All right, and we don't know that force of friction. So we got these two unknown forces here, and you go, oh no, what do I do here? Okay, well, let's continue with the problem and we'll see. Okay, we will be able to get that force of friction. Okay, and then so that takes care of free body diagram number one here. Okay, that takes care of this. The only change is basically that force of friction. Okay, well, you know, let's think it through. Does this change? M1g cosine theta? Well, no, because the weight of the thing didn't change, so that number stays the same. The weight of the thing didn't change, so that stays the same. Okay, the normal force still has to cancel that perpendicular gravitational component, so that stays the same. And Ft will change, but we don't know the number anyhow. Okay, so Ft is going to be a different value than we found a minute ago, but I can't tell you what it is. All right. And the other thing was that there's an extra force of friction. Okay, so there's the change. That's the only change right here is the change to free body diagram 1. What about free body diagram 2? Well, there's still the force of gravity, and it's still 60 newtons because nothing changed there. And there's still a force of tension up, and that didn't change. Now, you got to be careful. You know, you just solved this problem, and we just said a minute ago that this was 57.4. So you might be tempted to take the value from part A and use it in part B, but you're going to see that that number is going to change. Okay, because there's friction now in this, the Ft itself actually will adjust. Okay, so that's the kind of thing you got to be careful about. All right, yeah, there's a force of there's a tension force in part A and there's a tension in part B, but the value of that tension is going to be different. Like how big is it? It's going to change. Okay, and actually we'll calculate that too because we can. Okay, so let's do this. Let's do this problem. All right. So now you say, okay, let's go up here and see how much of this we can recycle. Okay, so let's copy all of this. All right. Whoops. Okay, there we go. See, the perpendicular component stayed the same. Okay, and in value too. Okay. The parallel component stayed the same. The normal force stayed the same. Ft is still unknown, but I shouldn't say it's still unknown. It's unknown in part B, and it's not the same value as it is in part A. Okay, and there's also Ff, force of friction, which is unknown. And at this point, you're going, well, it looks like there's two unknowns. Not quite, because I actually give you the acceleration. Okay, so let's put this thing together and see what we get. Okay, so take a look at the diagram now. Slightly different. Once again, we will have that Fn will cancel that. Okay, so those two are out of the game. All right, it's still accelerating uphill. Okay, I didn't say that explicitly in the problem, but I think it's kind of clear from context. All right, and so Ft must be bigger than what? Must be bigger than these two added together. Okay, so when forces are opposite of one another, they compete. So they like one will try to subtract from the other. When they're in the same direction, they add. Okay, so we don't just have Ft minus mg sine theta. We have Ft minus these combined two forces. Okay, so that's 51 plus Ff. All right, so let's go back here, and now we can write that F net is equal to the Ft, which is pulling uphill, okay, minus, and both forces downhill are adding together, so you've got 51.30 plus Ff. Okay, those are both both of these are pulling downhill, and so they compete with that Ft. Okay, so there you go. If you want to clean that up a bit, well, we will in a minute. Okay, now, all right, remember what you do at this point. Once you've got F net, the whole point of doing this analysis was to get F net and set it equal to MA, okay? And in this case, it's M1A, all right? Now, let's see if we can plug in numbers here. For M1, we have, well, it was 15. And for M2, sorry, for A, we have that it's 0.2. Okay, so this is different because last time I didn't tell you A, I expected you to find A. But now I'm telling you A and expecting you to find the force of friction. Okay, and so this is going to reduce to this. Let's get rid of that there. And of course, if we distribute the negative sign, you'll get that. Okay, so because it's negative this and negative that. Okay, that's going to equal. So that's going to equal 0.2 times 15. All right. Whoops. So it's 0.3. Yeah, sorry, 3. I mean, yeah, there it is. Okay. All right. And we can reduce this a little bit more, right? Because we can have that Ft minus Ff is equal to, so we've got this value from the one side plus 3, okay? And then finally, we've got this is equal to 51.3 plus 3 is going to be 54.3, okay? And there's our equation number 1. All right. Good so far? Actually, let me look in the chat here. Oh, I've got some all right, no questions. Okay, so let's continue here. Okay, so now let's take a look at the free body diagram for M2. Okay, now over here we're still in the situation where A is down, so we still have 60 minus Ft. Okay, and so F net is going to be over here. So this is free body diagram 2. Okay, we've got that F net will equal the Ft down, sorry, the 60 down minus the Ft up, and that's got to equal by Newton's second law, m2a, like that, okay? And we know that m2 is going to be, well, we know m2 because I gave it to you, but we know that a is 0.2, okay? And that's going to be 1.2, like that, okay? So cleaning that up a bit, we get that 60 minus ft is equal to 1.2, all right? And so that tells us that ft is equal to 60 minus 1.2. All right. What did I do? Well, I guess I subtracted 1.2 from both sides, and I added ft to both sides. Okay. And then that reduces to, that tells us that ft is equal to 60 minus, whoops, 1.2. And that's 58.8, like this, newtons. Okay. And there's our equation number 2. But equation number 2 is kind of easy because it's not really even an equation. You could just plug it immediately into equation number 1. And so we'll just do that. Sub into equation 1, like that. And we will get that ft, like that. But now we're going to put in 58.8 for ft, like that. And so we get that 58.8 minus ft is 54.3. So that means, sorry, ff. So 58.8 minus the force of friction is 54.3. And so ff is going to equal 58.8 minus 54.3, which is going to equal 4.5, like that, newtons. Okay, and there we go. We've got the force of friction. Now, we almost answered the question, not quite. I asked in the question, what is the coefficient of kinetic friction? Okay, but once you've got ff, you know that mu, okay, of kinetic friction, I can't do my little mu symbol, so I'll just write mu. Okay, so mu k is going to equal the force of friction divided by the normal force. And the force of friction we just found to be 4.5, and the normal force, we can go back up here. The normal force was that number right there. Okay, and so if I substitute in, just do it on my calculator. I get this value right here. Okay, rounded off to 3 digits. Okay, so there you go. There is the coefficient of friction. It's a small coefficient of friction. Okay, but you know, it's not 0. It's 0.0319. Okay, so there you go. Now, before we move on, let's take a look at that tension. All right, and compare it to part A. All right, so the tension in this question in part B was 58.8. So if we go back to the diagram here, all right, let me do this here in for part B. For part B, we found it to be 58.8, like that. For part A, we found it to be 57.5. Okay, and you go, well, does that make sense? Yeah, it kind of does, because you see this ft now is actually pulling a lot more because there's an extra drag due to friction. So ft is actually bigger in part B than it is in part A. Okay, but more importantly than that, notice what would have happened if we had accidentally used 57.5 for B, in part B. All right, rather than calculating it from scratch, then we would have gotten the wrong answer. Okay, so be careful about that. You know, you redo the problem. Don't assume that, you know, what you got from the first part carries over to the second part. Some of it does, but you have to rethink it. Okay, so, you know, like you say, well, not much changed here, but yeah, but we still rethought it. Okay, and so let me clean the diagram up a bit here. Okay, so over here, you know, we did rethink this and we said, oh, it doesn't change. Okay, we did rethink that and we say, oh, that doesn't change. We did rethink this and we said that, oh, that doesn't change. So those are the parts that did not change. Okay, we rethought this and we said there's still a force of friction, but on thinking upon what its value is, we realized we don't know that it's the same as in part A. Okay, so don't put a number there. Don't set it equal to 57.5, otherwise you would have gotten the wrong answer. And then of course there's an added force, which was the force of friction. Okay, but I think you would agree that the change in value of the force of tension, the tension force, that is subtle. Okay, so there you go. That is part B. Okay, and there's one more. There's a part C to this. Okay, and in part C, I say if the system doesn't accelerate at all, what is the coefficient of static friction? Okay, so if we go back to the diagram here, okay, in this case, let me see if I can clean it up a bit. I'm not sure that I can. Yeah, not well. Okay, let's see here. Let me clean it up a bit. Yeah. All right, there we go. Okay, good. Okay, so we're rethinking it from scratch. Okay, and so what's going on here? Well, we have still the force of so we're rethinking everything. We still have the force of gravity here in two components, and when we calculate those values, this number is not going to change. I don't have to write it in here because I've got it, but that value is not going to change, and that value is not going to change. Okay, we rethink this one. Yeah, there's still a normal force, and it's still got to equal that one. Okay, there's a tension, but we don't make any assumptions about its value. Okay, and there is another force. It's friction. It has to be downhill because this thing wants to go uphill, and don't assume its value. We don't know how big it is. It is static friction like that. Okay, so there's the free body diagram for mass number 1. Okay, here's the free body diagram for mass number 2. It hasn't changed either. The value of m2g doesn't change, but make no assumptions about the value of ft. Okay, so basically the same kind of thing. All right, so let's go back to this, and let's see what we can conclude, or what we have concluded, I should say. So back to free body diagram for number 1. Just cutting and pasting so I don't have to retype everything. All right, this is still the same, isn't it? Okay, the perpendicular component still in the same direction, same value, and so on. The parallel component is still the same. The normal force is still the same. The tension is still unknown, and the force of static friction, which we've been using Fs for that, that's also unknown. Okay, and there you go. Okay, so now what is F net? All right, so once you have identified all the forces, do the vector sum. What's F net? Well, the perpendicular component cancels F net, and now this thing is not accelerating either up or down, so it doesn't matter whether you choose up as the positive direction or down as the positive direction. We'll continue with up, and so we'll say, like, up we have ft, okay, like that, and competing with that, down we have the parallel component and the force of static friction, like that. Okay, now this is worth looking at just for a minute, because before I would always do the bigger minus the smaller, and at this point you say, well, but neither can be bigger or smaller because it's not moving, and that's right. So it doesn't really matter whether you subtract this minus that, or conversely this minus that. Both of them have to equal 0. And you go, why is it equal to 0? It's not accelerating, it's not moving. In fact, this is the first law. Okay, so this is it's the second law, but once a is equal to 0, it's effectively Newton's first law. Okay, so there you go. So yeah, it's not moving, so that's equal to 0, like that. Okay, so now let's just clean that up a bit. So we get that ft minus 51.3 minus fs must equal 0. Okay, there's our equation number 1. And we can't go any further with that. Okay, so let's take a look at the free body diagram for number 2. All right, and we convinced ourselves that most of that didn't change as well. So it's well, you know what? Let me just write it here. The net force, there's not much to write there. The net force is just going to equal. Let's look at the diagram again to remind ourselves. it's going to be the M2G, which was 60 newtons down. Okay, 6 times 10, so it was 60 newtons down minus Ft up. Okay, so it's going to be 60 newtons up, 60 newtons down, pulling down, minus the Ft up. And what's that got to equal? Well, it's not moving either, because we're in a situation of static friction. So that's equal to 0 as well. Okay, and so just cleaning that up a bit, 60 minus Ft is equal to 0, and that is equation number 2. Okay, and again, these double equals, I mean, that's just me trying to say because of Newton's second law. Okay, it's just an equal sign. All right, and now what? Well, we can add equation 1 and 2 together. So add equation 1 and 2. All right, add the left-hand sides, add the right-hand sides as we did before. So we've got this from equation 1 plus this from equation 2. And when we add the right-hand sides, you get 0. And so Ft here, positive Ft, subtracts against negative Ft there. So we just get that this is equal to 0. Okay, and now we have 60 minus, let me do it on my calculator, so 60 minus 51.3 is 8.7. So we get here that it's 8.7 minus Fs is equal to 0. And then it's pretty obvious that Fs is equal to 8.7 newtons. Okay. All right. So back to the diagram to see what's going on here. This force right here, that has to be 8.7 newtons, so that when these two add together, they will exactly cancel that one. And that one is equal to this one, which will exactly cancel that one. Okay? So Ft needs to be equal to 60, and it is. Okay? So in this case, like I didn't ask you to find Ft, but you know, from equation number 2, it's pretty obvious that Ft is equal to 60. Okay, 60 newtons. So now, you know, like if we really want to compare things between the 3 problems, or let's go back here, and we ask the question, you know, what's the difference between Ft between part A, B, and C? So in part A, it was 57.5 newtons. Okay, that's when there was no friction. In part B, when there was kinetic friction, it turned out to be 58.8 newtons, like that. And now in part C, when there is static friction and it's not moving, it's exactly equal to 60 newtons. And of course, it's exactly equal to 60 newtons because it exactly has to cancel out M2G like that. Okay, so you could see how like the tension actually changes depending on whether there's no friction, just enough to slow it down but not stop it, and then you know, static, which actually stops it. Okay, so all right, we didn't quite finish the question. We have the force of static friction, it's 8.7, but if you go up here, what I asked for was the coefficient of part C was the coefficient of static friction, and that's given the symbol mu subscript s. Now, it is not an equality. You can't say that is equal to. This is incorrect. You can't say that it's equal to this. Okay? It is equal to or greater than. Okay, now I don't have a symbol that does equal to and greater than, but we'll just use that. Okay, so mu s is I can't tell you its exact value. All I can tell you is its minimum value. It must be bigger than this number, and if it isn't bigger than the number, which I'll calculate in a minute, if it isn't bigger than that, then it will slide. Okay, so and it must be bigger than or equal to that. All right, and so we can plug in the numbers here. This one is 8.7, and Fn is 60, and so what's that equal to? All right, tell you in a second. It's equal to that number right there. Okay, so there's your coefficient of static friction. If you compare it to the coefficient of kinetic friction, which we found above, which was this number here, you'll see that it's bigger. Okay, like that. Sorry, my paste didn't work. Nah, okay. Sorry about that. But you can see here, this is like 0.145, and this one was 0.0319. Okay. Now, again, that doesn't tell you this. That isn't the value of static friction. That's it. That's the minimum value of static friction. Whatever the real value is, must be bigger. Okay. And if you want to understand that, think of mu(s) as kind of like stickiness, like how sticky the surfaces are. Okay. So they're sticky enough that they're not sliding. Okay. Now, if it's sticky at that level, it doesn't slide. If it's twice as sticky, it still won't slide. If it's 1,000 times stickier, it won't slide. Okay. So it's kind of has to have a minimum stickiness for it not to slide, and anything above that stickiness, it's good enough to keep it from sliding. Okay. So there you go. That's an application of Newton's 3 laws. Okay, along with questions of kinetic and static friction. All right, let me take a look at the chat here. Here we have a question. Why isn't Fn the same as before? It is. Fn the normal force? Oh, you know what? Thanks, Emily. You're right. I made a mistake. Right in here I put 60. It was just messed up in my mind. It was that's the tension. I put in the tension there. What I should have put in is Fn, and Fn is equal to that. So yeah, there we go. That's better, isn't it? Okay, so that number is caught a mistake. Yeah, it was it is the same. Fn is the same through all three of them. Here we go. It's this number here, which still, for theoretical reasons, must still be bigger than mu k. Okay, so yeah, here we go. It's 0.0617. Okay, I'm glad you caught that. Well, the mistake I made was I put ft there instead of Fn. Okay, so good. That should fix that. All right. So, well, that's it. Okay. If there are no more questions, I'm going to move on to Kepler's laws. Okay. So with Kepler's laws, there are 3 laws. All right. And again, I'm multiple choice test. I'm not exactly going to have you state them. But you should be able to choose between, some absurd options and the correct answer. Okay, so the first thing you should know is what the shape of orbits are. All orbits are ellipses. Okay, the Earth's orbit and the planetary orbits are close to being circles, very close, but they are still ellipses. They're still ellipses. They're just ever so slightly elongated. Okay, so the answer is ellipses. Okay, that's the shape of any orbit. To be more correct, the orbits are ellipses with the sun at one of the 2 focal points, because ellipses have 2 focal points. Okay, now the next thing is Kepler's second law. Kepler's second law is the one that no one can ever remember, because it has to do with how much area is swept out in an equal amount of time. Okay, and the better way to think about it, again, just qualitatively, you can't do calculations with qualitative statements, but it helps your intuition, is that the planets move fastest when they're closest to the sun. Okay, because the planetary orbits are ellipses, and because the sun is at one of the focal points, there's a part of the orbit which is closer to the sun, and there's a part of the orbit which is further from the sun. Planets move fastest when they're closest to the sun, and they move slowest when they're furthest away. Okay, so that is a qualitative statement of Kepler's second law. It's the third law that is the interesting one. Okay, and it's the one that we can do calculations with. So the third law, right here, I said use the data from this site here. We'll take a look at it in a minute to show that Kepler's third law works for Mercury, Venus, and Earth. Okay, so first of all, what is Kepler's third law? Well, Kepler's third law basically says that r cubed divided by t squared is the same for all planets. Okay, now you can either use that to calculate, if one of the r or t's are unknown, you can use that, or you could just verify that that's true, like you would in a lab. Okay, and so if we take a look at this website, okay, and this is kind of a neat website. It's basically just like all sorts of data for like a planetary fact sheet. Okay, and there's a lot of stuff here. Obviously, you don't need all of that information for this. You need well, what are the two things you need? Okay, R. R is the average distance from the planet to the sun. Okay, we call it the radius, but that's a little bit of a misnomer because remember these are ellipses. Okay, and so sometimes it's closer and sometimes it's further away. So it's actually the average distance. Okay, and T is the period. It's the time for the the planet to make one complete revolution. It's the year for that particular planet. Now for Earth, one Earth year is 365.2 days. Okay, 0.24 actually days. All right, so there it is. Okay, so this is the average distance to the sun, and that's the time it takes to make one complete revolution around the sun. Okay, the units don't matter as long as you're consistent. As long as you're consistent. So if we go back here, you could see the row that I have highlighted is distance from the sun. Here it's being measured in millions of kilometers. Okay, so for Mercury, the distance to the sun is this 57.9 million kilometers. Okay, for Venus it's 108.2 million kilometers, and for Earth it's 149 million kilometers. Okay, so the datum that I'm going to use in a minute is right from there. Okay, and then the other one is the period, and here it is. That's this row right here. Okay, so orbital period is the time it takes to go around the sun. Now this is measured in Earth days. Okay, so it takes Mercury 88 days. So you know, if you're just looking at your calendar and you count ahead 88 days, Mercury has gone once around the sun. For Venus, it takes 224.7 days. For the Earth, it takes 365.2. Okay, they rounded it off. It's actually 0.24. Okay, so 365.24 days, and so on. Okay, so let's see if we calculate r cubed over t squared for all of them. Do we get the right answer? Okay, so let me see here. I think I've got those numbers. Well, I've got the answers. Let me show you how you substitute it. I won't do it for all of them because it's kind of simple. Okay, so let's just do Mercury. So for Mercury, you take R, and R from that table there is this. Okay, now that's in millions of kilometers, but that's okay. We can we can work in units of millions of kilometers, and then you radius it to the third power, divided by the time it takes Mercury to go around the sun, okay, which is 88 Earth days. All right, okay, and so you're gonna, this r cubed over t squared will have funny units, but as long as we use the same units for all of them, we should be good. And the answer I get is for Mercury is this number right here. I did it earlier. I'm just going to cut and paste it. Okay, so there we go. There's the number. Okay, I'm not showing the units because the units are not MKS, and they're kind of weird units anyhow, because they're like in millions of kilometers cubed divided by days squared. I mean, what's that unit even mean? Okay, but we're comparing these numbers, and as long as we use the same units, even if they're weird units, we're fine. Okay, so for Venus, I did the same thing, only here I put the values for Venus, and I got this number right here. Oops. Like that. Okay. And then for Earth, I got this number right here. Okay. So if you compare these three numbers, and let's put them on the same line here. Mercury. They're pretty close, aren't they? They are pretty close. Okay, so Mercury is 25.065, Venus is 25.089, Earth is 25.103, and so on. Okay, now you say, well, could you do it for all the planets? Yeah, I didn't want to do it for all the planets because it's annoying to do all those calculations, and you get roughly the same number. Okay, you could do it for the asteroids that are orbiting the sun, you get the same number. Okay, you could do it for comets that are orbiting the sun, you get the same number. You get the same number for anything that's orbiting the sun. Okay. If you want to know why there's a bit of a deviation in here between these numbers, there is actually relativistic effects. Okay, general relativity, which is beyond the scope of this course. So, is Newton's third law perfect? No, because Newton's laws aren't perfect, and Newton's laws aren't perfect because when you have gravity and or when you're traveling close to the speed of light, then relativistic effects come into play. Okay, but pretty good, pretty good. Okay, so there you go. Historical note: why are Kepler's three laws important? They were guessed at. Kepler just guessed it. At those three laws, and he had data from another astronomer called Tycho Brahe. Tycho Brahe compiled all this data, and Kepler just said like what fits this data. Okay, just like you do in the lab, you go, well, what kind of function fits this? And he found his three laws, but he had no deeper explanation. Newton comes along, and with his three laws that we just studied a minute ago, plus the universal gravitational law, he's able to prove all three of Kepler's laws, and that's it. People say, well, there's this thing in the universe called gravity, and it's the same thing that makes an apple fall on your head. That's the same thing that makes the planets go around the sun. And so there was this kind of unification of different phenomena that had never been explained before. They'd been explained in Aristotelian terms, which were, I don't want to go into it, but just weren't very satisfying. Okay, so there you go. All right, so there's Kepler's laws. Okay, so let me see if there's any questions, and if not, we will move on. Okay, no, I don't see any questions here. Okay, let me just take a quick little break. I'm going to take a sip of coffee, and I'll mute so you don't have to hear me. There you go. And instead of a break, I'll drink some energy. Okay, two more questions and then we're done. Um, they're both about energy. Okay, and the first one, let's read it here. It says there's two parts. Okay, so the first part has no friction. A car of mass 1,000 kilograms is coasting in neutral. Neutral just means that all cars have neutral, but especially on a standard transmission, you could just put the car in neutral, and it'll just move along with at a constant speed. It'll slow down because of friction a bit, but the gas isn't pushing it forward. In other words, okay. See, if you're pushing on the gas, what you're doing is you're actually adding energy. You're turning some of the fuel energy, some of the chemical energy in the fuel into kinetic energy. Okay, we don't want any of that. Okay, so that's why I said the word coasting here rather than traveling. Okay, so it's coasting along at 100 kilometers per hour. It encounters a hill, and it's going to go uphill. Okay, it doesn't matter what the shape of the hill is or whatever. I want the vertical height that it goes up. Okay, we don't even really need a diagram for this. All right, basically what you have here is, I'll do a diagram anyhow. Will I do a diagram? Let me see here. Let me bring up Pinta again, and yeah, we could do a quick diagram. Let's do it. I don't know, just not to be confusing. Let's see, is this going to work? Yeah, good. Okay, so it's a really straightforward diagram. Basically, you have the car here on level ground. So I don't know, what color is our car? Red. There you go. There's our sporty red car with red wheels, and it's moving along here and just goes uphill like this. And it doesn't really matter what the shape. That's a really steep hill. Okay, anyhow, at some point, it's gonna just get up here, and it's gonna get to its maximum height here like that. And sorry, it's a funny looking car up there, but okay, you got the idea. So the car is up here, and it stops up here. It stops, and I want to know, what is this height right here? What is the maximum height it gets to? Okay, what is the maximum height it gets to before it stops and starts to roll back down? Okay, so let's do that problem. Okay, so see, let me make sure I'm reading it right. How high does it climb vertically before it stops and starts to roll back down? Okay, good. Now, again, on the test, whenever you have MGH, which is the potential energy due to gravity, I'm going to have to tell you where the zero is, because without telling you the zero, everyone will get a different answer. So if I ask you for the energy, and usually I break the same one question, I'll break up into several. One problem will break up into several questions. Okay, so one of the first things is like what the energy is, and so for this one, we'll just take h equals 0 at the ground level here. Okay, so over here we could just say that this is h equals 0. Okay, like that. All right. So if you do that, you say, well, what's the energy initially? And the energy initially, the energy right here, is going to be all kinetic energy. Okay, so it's all kinetic energy here. And then by the time we get here, okay, it actually stops, right? Because it's going to start to roll downhill. So V is 0. And if V is 0, the velocity is 0, there's no kinetic energy. It is all potential energy. Okay, so this is a pretty easy problem, but it's worth seeing how this works. I'm going to add friction in a minute, but initially, okay, so you could say E, we can call it EA. So let me go back to that diagram and label it. Okay, so this is going to be here. This is like picture A here, like that. And this one up here, this one's going to be B, like that. Whoops, lowercase b, to be consistent. There we go. All right, and EA is going to be, we can write down everything, but parts of it are going to be 0. 1/2 mv squared, that is the kinetic energy, plus mgh is the potential energy. Okay, at A we know that it's all kinetic energy, so we know that this mgh is going to be 0, but it doesn't hurt to write it there, just as long as you realize that it's going to equal 0 in a minute. All right, and so it's 1/2. M is 1000, and V is 100 kilometers per hour. And so before we do that, maybe we should do a conversion. V is 100 kilometers per hour. That's not MKS, right? So kilometers per hour to meters per second, we've done that so many times, you just divide by 3.6. Okay, and it's like multiplying by 1,000 because a kilometer is 1,000 meters, but the dividing then by 3,600 because there's 3,600 seconds in an hour. Okay, and so over here, this is going to equal 27.7777 meters per second. Okay, too many digits, but good enough. Okay, and that's squared like that, and then plus, well, M and G, they're not 0, but H is 0, so there you go, it's 0 like that. Okay. So what's that equal to? There's your total energy. And I should have that calculated somewhere. I got this number right here. Okay. And let me actually check it. Is that right? It's worth checking just to make sure that I didn't make a mistake. 385,800. Yeah, it's slightly off, but it's good enough. Okay, I got there it is. Good enough. Okay. All right. So on a test, though, you might see it this way: 386 kilojoules. Okay, capital K kilojoules, like that. Okay. Why? Well, because if I divide 1,000, that'll drop off, and then rounding off, it'll be 386. Okay, kilojoules. All right, and a joule is really small. Okay, and so usually you measure energies for macroscopic things in kilojoules. Food energy can be measured in calories, capital C calories, which you'll learn about in chemistry, or in kilojoules. Okay, and in Canada, for instance, those food labels, they'll actually have the energies in kilojoules. Okay, but we'll come back to that next semester when we actually do heat, because that's where it's more appropriate. Okay, now great, that's the energy at part A. What's the energy at part B? Well, you can use the same formula, okay, but now the quantities are different. At B, there's no velocity, and so that part is 0, but there is a height, and so that part is not 0. And so this was I just wanted to do a really simple example that showed how energy went from kinetic to potential. Okay, pure all kinetic to all potential. Okay, I'll show you what another place where that happens, and just so you can get a better intuition in what's going on here. So the velocity is 0 there. Okay, so that's equal to 0 plus and you know that EB is the same. Okay, it's this number right here. You go, why is it that number? Well, because energy is conserved, there's no friction. Okay, So EB is the same as EA. That's kind of the point of conservation of energy. 1/2 mv squared, well, it's not moving, so there's no kinetic energy. And we got mgh, and m is 1,000, g is 10, and there's h. Okay, and that gives me an h of, take this number here, divide it by 10,000, 1,000, and then divide it by 10. Okay, and it gives me this height right there. Okay, and that would be meters, and on the test, of course, 3 significant figures like that. Okay, so it actually rises about 38.6 meters, which, roughly speaking, that's like 100 feet. Okay, so it's like this thing goes 100 feet vertically before it stops. And just to be very clear about what that is, okay, that's not 100 feet like along the path here. So it's not like let me do it in purple here. It's not like 100 feet along that. Okay, that path, the purple path here, it's 100 feet up, vertical height. Okay, so in other words, this point B is 38.6 meters above point A before it stops. Okay, now that is assuming there's no friction. So this leads us to part B, and in part B it says the car actually only rolls uphill 15 meters. All right, and that would be like roughly 50 feet or something like that. Okay, and no, less than 50 feet. So you say, well, why did that happen? Why didn't it roll up quite as far? Okay, and the answer is because there was friction. Okay, so how much energy is lost due to friction? Now in this case, you still have that the energy initially is the same, so you still have this. All right, right here, let me cut and paste that. You still have the same initial energy, but the final energy is different. Okay, still the same formula, but the numbers are different. Okay, why? Don't put that EB is the same as this. Okay, so don't do that. Okay, substituting for EB, because energy was lost due to friction. Okay, and better stated, energy is converted to heat, which we don't know about, so it looks like it's lost. Okay, like when you lose your keys, they don't disappear. You just don't know where they are. Okay, that's kind of the situation we're in here. It's not that the energy disappeared, we just lost it. We can't account for it with the physics that we have. We need this extra piece of physics. Okay, so so don't do that. Okay, we have EB here. It still comes to a halt. Okay, so it's still zero velocity, which means no kinetic energy, plus, and now the mgh is going to be 1,000, 10, and it only achieves a height of 15 like that. Okay, and so this is going to equal, EB is going to equal 1, 5, 1, 2, 3, 4. Is that, do I have enough zeros there? 1, 2, 3, 4. 150,000 joules. Okay, yeah, it looks like I got it right, or 150 kilojoules. Okay, so that's how much energy it now has if it only rises a distance of 15 meters before it stops and starts to roll down. Okay, remember, when it stops, it's got no kinetic energy, so it's all potential energy, and mgh for 15 meters is only 150 kilojoules for this car. Okay, and you go, well, what happened? Okay, so delta E is the energy lost. So the energy lost is, you do, like for delta, you do the final minus the initial, like that, and that's going to give me a negative number. Let me work that out on my calculator. Could do it in my head, but I'm lazy. Technology makes us lazy. There we go. So it's negative 236 joules. Okay, so it's negative 236, kilojoules. Okay, all right, there you go. And so that answers how much energy is lost. Okay, now reread the question again. How much energy is lost due to friction? That's that part. Okay, but then the other part of it is, if this energy was lost over a distance of 2 kilometers, what is the force of friction? Okay, now what that means, being lost over a distance of 2 kilometers, where would you see that in the picture? So this picture is not to scale, but if you were to just like say, okay, if I travel here along the road and there's friction. That's why I'm doing it a jagged line here. I'm traveling here, that total distance, the total distance of that purple line is 2 kilometers, okay? Well, you can work out how much friction there is because there's work due to friction, okay? So this energy, this delta E, is actually equal to the work due to friction, and the work due to friction can be calculated as minus FF, that's the force of friction, times D, which is the distance over which the force acted, okay? Now the work due to friction, that delta E, that's this number right here, so we can put that down there like this, all right? So there's that delta E, which is the work due to friction. That's equal to minus, we don't know FF, because that's what we want to calculate, and D is 2 kilometers, okay, we need it in meters, so that's 2,000 like that. And you'll notice that the negative signs cancel. There's a negative sign there and a negative sign there. And you will get that FF is equal to, let me do it on the calculator. It's like 100 something. There you go. It's 117. I would do on a test 118 newtons, okay? So what that means is that all along that purple path, okay, all along this purple path here, on average, there was a force of friction of 118 newtons, okay? Now 118 newtons is, significant, but not for a car, okay, not for a car. And that friction might be coming from the wheels, it might be coming from the air, whatever, but there it is, okay? So there you have an example of conservation of energy versus energy lost due to friction, okay? Now, I have to say that this is simpler than the one I did in class. I usually try to do harder problems in these reviews, but I wanted to do a simpler problem to show you a few things, okay? So let's go back to this diagram. We could see here that, you have all kinetic energy and then all potential energy. That happens a lot. That happens with the oscillator, okay? And so that's what inspired me to do this. So with an oscillator, what do you have, okay? So with an oscillator, I'll draw it up here. You have a mass which is simply bobbing back and forth like that, okay? So here's like a mass, and the blue line is the path here. Okay, and so it moves, one way along this path, and then it bobs back the other way like that, okay? And this is a very typical kind of a situation where you have all potential energy becoming all kinetic energy and then back and forth again, okay? So here you would have at the endpoints here like this, where it stops, at the endpoints here where it stops, it's just like this, isn't it? Okay, so where it stops at the endpoints, it is all potential energy. Okay, conversely, and then of course, obviously on the other side here like that. Okay, so where it stops at the endpoint, it's all potential energy. Conversely, in the middle here, right in the middle here like that. Okay, that's where it's all potential energy. Oh, sorry, I said it wrong. That's all kinetic energy here. Okay. KE. All right, which is just like this one down here, okay? Could have drawn a little red line between these. All right, very typical situation when it comes to conservation of energy. You'll have things where, like dynamics where the energy is all potential, other places where it's all kinetic. And then you might say, well, what about over here? Is the energy kinetic or potential there? A little bit of both. It's a mix of both. And so over here, right there, it's a little bit of a mix of both. Okay, so there you go. There's a parallel between our simple harmonic oscillator problems and our problems with things going uphill or downhill. Not to belabor this, but just to help your intuition a bit more. If you take something like a bowl. Okay, and it doesn't even have to be like a round bowl. It could be like any kind of a weird shape here like this. And you take a ball like this and you put it at some height here like this, okay? And I know there's friction in the real world, but we're going to pretend there's no friction. What's this thing going to do? Up here, it is all potential energy. So all PE. In other words, don't push it when it's at the top there. You're just going to release it from rest there like that. It's all potential energy. Then what's this thing going to do? The ball is going to roll. Let me do it in purple here. It's going to roll downhill, 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 and then uphill like that. By the time it gets up to the same height, the energy is all potential again. It's all potential up here like that. And you go, well, at what point is the energy all kinetic? And you guessed it, right down here. It's all kinetic. Okay. And so there's a lot of these kind of physical situations which are similar to the oscillator. Okay. Their equations for calculating the total energy might be different, but they're similar to the oscillator in this respect. They'll go from being all potential to all kinetic to all potential to all kinetic to all potential, and back and forth. The energy will just keep sloshing back and forth like that. Okay, and so well, there it is. Okay, that's what inspired this problem. All right. Anyhow, last question, and then we are done. So that's this question right here. A mass of 1.2 kilograms is attached to a spring with K equals 10 newtons per meter. Okay, so far everything in MKS. Okay, and at a certain point in the cycle, it is found that the oscillator has an amplitude. Oh, I shouldn't have said amplitude. At a point in the cycle, the oscillator is at position. Okay, is at position 0.5 meters and has velocity. Okay, does that read right? Let me read it again. A mass m equals 1.2 kilograms is attached to a spring with K equals 10 newtons per meter. At a certain point in the cycle, it is found that the oscillator is at position x. I don't need to put x. It's at position 0.5 meters and has velocity 1.5 meters per second. Find the total energy, find the amplitude, find the maximum velocity, and the period of the motion. Okay, so let's see if we can do that. All right, so the first thing is that you'll notice is that it's at this arbitrary point in the cycle. In other words, going back to that diagram, we're neither, looking at the diagram right here, we're neither at the endpoints nor we're at the middle. We're at some arbitrary point, like where the black dot is. Okay, so you can't use the equation for the total energy at the endpoints, which is the 1/2 Ka squared. You can't use the equation for total energy in the middle, which is the 1/2 mv max squared. You have to use the generic energy equation here, okay, for an oscillator. And that generic equation is E is equal to 1/2 mv squared plus 1/2 kx squared, like that. Okay. All right, good. So let's see if we can get that total energy. All right, so what do we have here? For m, did I give you m? Yep, 1.2. And everything is in MKS in this problem. All right, and what about v? Well, at this particular point in the cycle, the velocity is 1.5 meters per second, like that. Plus, okay, so there's our kinetic energy. All right, plus 1/2. K, I told you, was 10 newtons per meter, so we'll put it in here, 10 newtons per meter. Okay, and finally, the position, x, okay, it's not the amplitude. I don't know, I accidentally wrote amplitude here. It's the position it's at a position 0.5 meters, like that. Okay, so that means that from equilibrium to where we're looking at this thing, it's 1/2 meter. Okay, and at that particular position, it has this velocity there. Okay, so I'll spare you all the details. I'll just cut and paste this into my calculator and give you the answer. And turns out to be 2.6 joules. Okay, there you go. 2.6 joules. That's the total energy. Where is that the total energy? Everywhere in the cycle, including the endpoints and in the middle. Okay, so now when I say here, find the total energy, we got that. Find the amplitude. You go, aha! Now I can use this equation. E is equal to 1/2 Ka squared. Now notice that 1/2 Ka squared looks an awful lot like that 1/2 Kx squared, and it is, because when you're at x is equal to a, v is 0. So if you take all you have to do is really memorize this equation, because if you set x is equal to a here, then v is equal to 0, and you reduce to that. Okay. Now energy is conserved, which is kind of the point of all these problems. Okay. And so that E here is 2.6. All right. And then we have 1/2 We know that k is 10, and the unknown is a squared, which is what we're trying to solve for. So we get 2.6 is equal to 5a squared, like that. And that tells me that a is equal to, and I'll just do that for you on my calculator, 2.6 divided by 5. And then take the square root of that. And I'm getting this number right here. Okay, meters. All right. So 0.721 meters. Let's see if this makes sense before we go on. Okay, so that's the amplitude maximum displacement from origin. Okay, well, earlier we found that it was at 0.5 meters. So could it reach the 0.5 meter point? Yeah, absolutely it can, because it will stretch as much as 7.21, and 0.5 is smaller than 7.21. So far everything is consistent. Okay, all positions must be less than 0.721. Okay, because the amplitude is the maximum that x could be. And so an x of 0.5 certainly is consistent with a maximum of 0.721. Okay, great. That answers that question. So that question was find the amplitude. So we found the total energy. We found the amplitude. What about the maximum velocity? That happens in the middle of the cycle. Okay, so that's, again, if you go back to this, it's in the middle of the cycle. The middle of the cycle equilibrium is where x is equal to 0. So this falls out. So when v is equal to v max, you have this term with v equals v max here, like that, and the potential energy term drops out. So 1/2 mv max squared, like that. Okay, well, energy is conserved, so 2.6 for the energy. Okay, times 1/2. M, I told you, was 1.2 kilograms, so 1.2. And Vmax is unknown, but that's what we're trying to solve for. Okay, and so what's this equal to? All right, let me do that on my calculator here. 2.6 multiplied by 2 divided by 1.2, and then I take the square root of that, and I get this number right here. So Vmax is equal to 2.08 meters per second. Okay, put a letter score there. Okay, so there you go. That's Vmax. Again, ask, is that consistent? That's the fastest this oscillator will ever go. So if we go back up here and we take a look, and we see that at some point in the cycle it was traveling at 1.5. Is 1.5 less than the maximum? Yes. Okay, so again, it's consistent. All right, so it's good to check that you're within the right limits. This oscillator, the fastest it's going to be going is 2.08. And so will it ever obtain a velocity of 1.5? Yeah, it will. Okay, all right, great. And then the final part was find the period. Okay, now for the period, you go, well, how do I do that? So always remember that there's these two quantities. There's the period, and then there's this omega, which I'll write it out. Okay, well, actually it looks like a W, but it isn't a W. Okay, W is used for other things in physics, so we really should try to write it as an omega. On the test I have actually the omega symbol, but in my text editor I can't do it very easily, so I apologize for using a W instead of omega, but there it is. Okay, let's just pretend that W is omega. Okay, and there's a very simple relationship between T and omega. Okay, omega is this angular frequency, T is the period, and the relationship is that it's equal to 2 pi divided by omega, like that. So the period is equal to 2 pi divided by omega, like that. Okay, so and then 2 pi, so as soon as you know omega, you don't need anything else. You've got T. Okay, but the thing is how do you get omega? And omega is equal to the square root of k divided by m. Okay, and for the calc students, that actually came out of two things. If you take Newton's second law and you combine it with Hooke's law, which is the F is linearly proportional to x, you put those together, that just comes out as the frequency of the oscillation, or the angular frequency of the oscillation. Okay, which is kind of a remarkable result. All right, so yeah, the calculus gives some insight into what sets the frequency of an oscillator. Okay, um, okay. So what's this equal to? So it's the square root of K. I said was 10. M was, I forget now, 1.2. Yeah. So K was 10. All right, and M was 1.2 here. All right. So we've got 10 divided by 1.2, like that. And so omega is equal to, let me work that out. Where's my calculator? Here it is. So this is square root of 10 divided by 1.2. And it turns out to be this number right here. Actually, it rounds up to 9 like that. Okay. And if you're wondering what the units are, it is a frequency. And so that's like 1 per second. Or you will see this more often than not as hertz. Okay. But I don't know if it's an unfortunate thing that we call it hertz. It really is just per second, 1 divided by second. Okay. Hertz was a physicist that worked on frequencies. Okay. And so that's why, anything that's measured in frequencies, we measure it in hertz in his honor. Okay. So now T is going to equal 2 and pi is 3.14159. Okay. And more digits than we need, but good enough, and 2.89 like that. And let's see what this works out to. All right. All right, there we go. And that's too many digits, so we'll just round it off to that. Okay. So 2.17 seconds. Okay. And just to remind you, what is this period? Like, what does it mean? It means the time it takes for the oscillator starting at a point to make one complete cycle and then come back to the same point that it started. Doesn't matter where in the cycle you start, as long as you start at that point, you go through the full cycle and come back to the same point. The time it takes to do that is called the period. Okay. Just like the period of the orbit or whatever. Okay. So there you go. Did we answer all the questions? Let's read it again and make sure we answered all the questions. You should always do that on a test because, well, with a multiple choice, chances are you won't miss something. But, one of the things when I used to give out tests where people would write out their answers, they would always miss part of the question because they got so caught up in doing the problem that they would kind of miss something. Let's see here. So I give you some information. Find the total energy, the amplitude, maximum velocity, and period. Okay. So here's the total energy. Okay. Here was the amplitude. Here was the maximum velocity. And finally, the period of the motion. Okay, let me take a look in the chat here. And no new questions, okay? And so let me just say, is everyone okay? All right. If we're done, then we're done. If you have any questions, I'll hang on and answer more questions. Otherwise, I'll just bring the live stream to a close. All right, I'm not seeing any more questions. So let me just say goodbye to everyone and good luck on the test. Bye-bye.